We are now going to start our study of measures of spread, and particularly the range and standard deviation of a set of data. But first, let's recall measures of central tendency. So you've got two groups here. Group A, these are the salaries of the 5 people in that group. Group B, these are the salaries in dollars of the 5 people in that group. So to recall, the measures of central tendency that we are interested in this class are mean, median, and mode. Why don't you take a moment, pause this video, and do the computation for the mean, median, and mode for each of these groups individually. Once you've done the computations, Group A, you'll find, has a mean of 4,500, or 45,000, excuse me. It has a median of 45,000. And it has a mode of 49,000. With Group B, it also has a mean of 45,000, a median of 45,000 as well, and it does not have a mode. So aside from the difference that this one has a mode of 49,000 and this one does not have a mode, they have the same exact mean and same exact median. So would you say, if you looked at these two sets of data, that they're essentially the same? Because they have the same mean and median in each of the two groups. I'd say definitely not. This one here in the blue appears to be significantly more spread out than does the Group A salaries. So measures of central tendency are very important, but they're not enough. We need to include measures of spread. Again, measures of spread will tell you how spread out the data is, and the two that we focus on in this class are range and standard deviation. First, we'll start with the measure of spread known as the range. It's a very simple computation. The range of a set of data is simply the difference between the max data value and the minimum data value. So for Group A, we've got a maximum data value of 49,000 and a minimum data value of 39,000, leaving us with a range of 10,000. So that means there's a spread of $10,000 between the lowest paid person and the highest paid person. But with Group B, the highest paid person gets paid 60,000, minus the lowest is 25,000, giving us a range of 35,000. So the difference between the highest paid and the lowest paid in Group B is $35,000. $35,000 is a much larger range than is a range of $10,000 in Group A. So this means Group B's data is spread out more than Group A's is. However, this computation alone is not as mathematically powerful as what we call the standard deviation. Let us now take a look at that. Let's first go through the computation of finding the standard deviation of the salaries in Group A, so you can see how the computation is done, and then we can talk in a bit about the meaning of that computation. So first thing, notice over here we've got two formulas. One formula is for the population standard deviation, one is for the sample standard deviation. So again, if you have all the data that you're interested in, then you'd be computing a population standard deviation. This Greek letter right here is also sigma, the lowercase version of the capital sigma that looks like this. The lowercase sigma represents the population standard deviation in statistics. Then we also have the sample standard deviation. When you take a subset of the larger population and compute the standard deviation of that set, when you use that standard deviation to make a prediction about the larger population, this is the computation that you should do. And this lowercase s is what we use to represent the sample standard deviation. So we've got two formulas here, depending on whether you're working with a sample or a population, that are fairly involved. We need to go through how to do these computations. Let's treat this data like it is population data. So we are going to use this formula to find the standard deviation, and we're going to do it for Group A, so specifically these data values. You should also do the computations for group B to see if you can do this computation on your own. Let's first recall that mu represents the population mean, X represents the raw data values, and uppercase N represents the size of the population. So you may recall mu is 45,000. That was the mean of those 5 salaries. And N is 5 because there are 5 salaries. To find the standard deviation of the population, sigma, we've got to run through this computation. By the order of operations, we would first want to do this subtraction, meaning we want to take the data values and subtract the population mean from them. Then we'd want to square those differences. And then to get that numerator, we want to add them all up. That's the meaning of the capital sigma. We'd add all those squares up. Then we'd finally divide by n, and I shouldn't say finally because there's one more final step, which we take the square root of that number is the very last thing. So let's find the differences between the raw data values and the population mean. These are called the deviations. So 39,000 deviates from the mean by negative 6,000. If you take 39,000 minus 45,000, you get negative 6,000. 43,000 deviates from the mean by negative 2,000. 43,000 minus 45,000 is negative 2,000. 45,000 does not deviate from the mean at all. So 45,000 minus 45,000 is 0. And 49,000 is 4,000 above the mean because 49,000 minus 45,000 is 4,000. These are all our deviations. So not only does it tell you how far it is from the mean, but it tells you the direction. Hence, these ones are negative because they're below. These ones are positive because they're above. And this one is at the mean. However, you might be thinking, okay, once you've got these deviations, let's find the average of these. But if you took the average of these deviations, you would see it would come out to be 0. So these deviations would always average out to be 0, so that doesn't have any meaning for us. And the reason the average comes out to be 0 is because you have the same amount in the negative direction as you do in the positive direction. So instead, let's square them. By squaring them, you'll make them all non-negative. So that is our next move, is to square those differences. The square of negative 6,000 is 36 million. The square of negative 2,000 is 4 million. The square of 0 is 0. The square of 4 million is, or the square of 4,000 is 16 million. And again, we have 16 million here. I'm not sure why I have this additional column here. Please ignore this. I'm not going to re-record the video with that not there. That's just a repeat of the previous column, so that is not needed. The next thing we need to do is take the sum of these squares. So we need the sum of all these numbers here in this column. And we get 40 million plus another 32 million is 72 million. Then, according to the computation, our next move is to divide this by n. So we're going to take 72 million and we're going to divide it by n, which is 5. 72 million divided by 5 is 14,400,000. And then finally, that is not the standard deviation. The standard deviation ends with a computation of the square root of that quotient we just got. So we need to take the square root of 14,400,000, and that is our standard deviation of the population. And this is approximately equal to $3,794.73. So the population standard deviation of the salaries in Group A is approximately $3,794.73. You should now pause this video and see if you can get the population standard deviation of the Group B salaries. The population standard deviation of the Group B salaries is $12,790 approximately. So as you can see, the set that looks much more spread out has a significantly larger standard deviation than the other set. The Group B salaries has a standard deviation of over 12,000, whereas the Group A salaries have a population standard deviation of less than 4,000. So the larger the standard deviation, the more spread out the data is. However, you might be wondering, what exactly does that specific number mean? What does the $12,790.62 mean specifically? We need to develop a few things a bit more before we can talk about that.